Hello and welcome to the last video in the series Special Relativity in Three-Dimensional Geometric Algebra. In this I will be working on two problems which are related to each other, but basically demonstrating how things operate in, or how you would solve problems using this framework. And I hope that it shows how much easier it is to do, or to get started on problems and just to carry them out in this. So the first problem: suppose there is a lab frame and some rest frame moving at a constant velocity v equal the magnitude of v only in the x direction with respect to the lab frame. Let a equals all of this be the position of a point particle as seen in the rest frame. Given that cosine of phi is equal to gamma and that v over c is equal to b, or beta, show that the position as seen in the lab frame is a prime, the inverse Lorentz transformation, and then no effect. So the first thing to know is that this is moving in only one constant direction, and it's a point particle. There is no rotational motion involved. So given a Lorentz transformation or a Lorentz rotor, which generally has a hyperbolic component and a rotational component. In this, there's no rotational component, so we're just dealing with a Lorentz boost. And this is a constant motion, so it's constant motion, meaning that this Lorentz motor or Lorentz rotor will not change in time. So that is, we have that the change in time of this Lorentz rotor is 0. So that means we can use the definition that was given when the Lorentz rotor was first introduced in my videos. That is 1/2 phi, then the direction of motion. The direction of motion happens to be sigma x, so we can just write that. Therefore, this right here is a Lorentz rotor. And paravectors map, so we can map a paravector by saying that A prime is equal to the Lorentz rotor A, and then lambda dagger. So this right here is the equation that we need to do, or we need to work on. A is given to us up here, and our lambda is right here. So we can write this out as E 1/2 phi sigma x, then times CT sigma t plus x sigma x plus y sigma y plus z sigma z, end parentheses, and then because the reversion does not affect vectors, we end up with just the same 1/2 phi sigma x. Now we can pull all of these. So let me just copy this. We can now distribute these. So the next step is distributing them. So we have that CT sigma t. But if you remember from the fact that paravectors, the sigma t here, this is just sigma t is equal to 1. So this is a scalar. So we can just move this to the other side here. So then we can have that there and move this here. But these will just combine right here. These exponentials will just combine, and we end up with phi of sigma of x times ct sigma t. Now we can distribute this over to x sigma x, have it in here again, plus the same thing, y sigma y, plus this z sigma z. So this right here is the equation. Now we can simplify this even further. So if I just E phi sigma x ct sigma t, well, this x right here means that this exponential can commute with this sigma x right here. So it's possible, or if you want to think about it this way, the exponential, so if you have some e to some vector, I'll just unit have vector, then it's equal to 1 plus that vector plus the rest of its expansion. So if you have e vector and then some the vector here, then that's equal to all of this 1 plus v plus dot 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 v. You can distribute that through, and for example here we'll end up with v plus v times v all the way, but then we can just pull out the v to the left. So 1 plus v all the way. So we end up with v being able to commute with its with the exponential of v right here. So this and this means that they can commute. I will put this over here, and I'll move this here. Or actually, do this, do that. Move this there. So we can do the exact same thing. We can have this commute with this to come over here and combine to give us a full exponential. So e phi sigma x, x sigma x. Now, can we do that? Can we do that with these right here? Well, it's not quite the same. What we end up happening is that we end up having a sigma x and a sigma y times each other, but this is equal to negative sigma y sigma x. So you end up with a negative sign in this one right here. If this moves to the left, then this picks up a negative sign due to the fact that it anti-commutes. And that can be seen through this right here. I'll draw, or I'll write out the anti-commuting version of this. Let me give it a different color. A color that I use. And if we have all of these V's, if we have sigma x and sigma y, we end up with sigma x here, sigma y, which then end up being sigma y, and then sigma x, sigma y, which ends up being sigma y minus sigma y, sigma x, and then you end up with corresponding negative signs in the other terms here, so you don't need to write it out here, but you end up with corresponding terms there. And this means that in the end, you can pull out the sigma y on the other side, but you have 1 minus sigma x plus the corresponding terms, and this is defined as e to the negative sigma x. You have a negative sign now. So when you have this swap sides with it, then it's negative. So as we're going to swap sides with this, we're going to end up with a negative sign. So we get e to the 1/2 phi sigma x, e to the negative 1/2 phi sigma x, which this cancels out. This just becomes 1. So we can write y sigma y, and the same exact process happens for this. So we end up with only z sigma z. So the only two terms that are affected by the Lorentz transformation are the time component and then the component in the direction of motion. So this can be expanded. So you can have cosine of phi plus sigma x sine of phi ct sigma t. Then plus the same thing times x sigma x. Then plus these. You can multiply this through. And what I'll do is I'll group up all the terms that end up with the sigma t and all the terms that end up with the sigma x. And I'll put all the sigma t here and all the sigma x there. So sigma t times a scalar just gives something with sigma t in it. So we're going to end up with cosine phi, and then plus, or cosine phi plus, and we're going to come over here. We've got sigma x times sigma x. By definition, it squares to 1 because it is a unit vector. So we end up with plus sine of phi x. And forgive me, I forgot to write the ct here. Ct. All of this sigma t. So then the term that'll give us terms with sigma x in it are this term and this term. By multiplying those out, you can see that you have cosine phi of x plus sine of phi times ct. All of that times sigma x, and then the other terms. This right here, this sine, should be purple. Now there should be a similarity seen between this and this. We are almost there, and we were given that cosine of phi is equal to gamma, and that v over c is equal to beta. So we can replace all the cosines, but how do we get beta in here? Well, there's another little bit of arithmetic that you can do on the side, and that is through the definition of the arctangent, or sorry, not arctangent, hyperbolic tangent. And that is that this is equal to v over c, right? Because of the original definition of the inverse tangent being v over c. So from this we can get this. But this is just sine of phi over cosine of phi. is equal to V over C. Well, this implies that sine of phi is equal to cosine of phi times VC. And so we have that we can replace cosine with gamma and V over C with beta. So we can just write cosine phi is equal to gamma, and then sine of phi as equal to beta gamma. So let's go in here and then make the substitutions. So you can have gamma CT plus, and then I'm going to put another gamma beta, then x sigma t plus gamma x plus gamma beta CT sigma x plus all the other terms. And finally, we can put it into simplified form by pulling out the gammas. So we have CT plus beta x sigma t plus gamma times x plus beta CT sigma x plus all the other terms. And this is the proof. So I'm going to put a little end of proof logo or symbol, that's the right word. An end of proof QED symbol right here. So then this right here is the problem and its solution. Now let's move to the next problem. Suppose that this point particle that we just were dealing with has charge Q. Then the rest frame electromagnetic field is just an electric field given by Coulomb's law. And Coulomb's law just says that the field is going to spread out from the point mass. So if you have a point charge, then the field is going to go, let me draw that better. The field is going to go out like this. If it's positive, it's negative. If it's negative, then the arrows go in. But that's all that this is saying, is that there's a point charge. Find the lab frame electromagnetic field F prime given that bipyrovectors, and recall a bipyrovector is an element in the algebra that has a vector and bivector component. They transform through this law using the Lorentz rotor, but instead of taking the reverse, you take the Clifford conjugate. So the first goal here will be to just rewrite our lambda. We know that we're dealing with 1 over 2 phi sigma x. And our next step will be to just ignore this for now. And we're going to rewrite this E in its Cartesian coordinates. So we can rewrite F, the original field, as equal to E, this vector E, which we can then break into an x component and just say that that it has that value at position r, and that sigma x is that value, and plus E y, the value at r of sigma y, plus E z, the value at r sigma z. So this is now in Cartesian coordinates. If you want to, on your own paper, you can expand this by replacing this r squared down here with the respective Cartesian coordinates. But since that would require me to write a ton, I'm just going to do the rest of the problem with these coefficients standing in for the Cartesian coordinates or expansion. So the next step is to look at the transformed field. So f prime. So this will be lambda f lambda Clifford conjugate, which is e to the 1/2 phi v, but this v is just sigma x. And then we have this, all of this in here right now. And then the Clifford conjugate actually does affect vectors, so we end up with the negative 1/2 phi sigma x. So this is what we now need to multiply through. So if we put this right here, or let me copy this, copy that, keep pressing cut on accident, then move this here, then we have a negative sign, then plus this, and then plus this, plus this, and then sigma x. So you end up with this. Well, this has sigma x up in the exponent, and this is sigma x, the only vector in between the sandwich. And we know that if the vectors are the same in the exponent and on there, that they commute. So that means that when we come down here, we can just literally bring this one over here to cancel with that. So we end up with Ex r sigma x. So it turns out that the electromagnetic field actually is unaffected in this direction, the direction of motion. Can we do that for the others? Well, we can bring them over, but remember that actually they anti-commute. There's a negative sign there. But because there's already a negative sign, the negative sign will go away, and we will just end up with e to the phi sigma x. And then plus this, and then plus this again, e to the phi sigma x, plus this. The same thing happens for this component. Then we can bring this down. And then expand this out like we did before. But instead of using the cosines and sines, I'm going to directly go to this notation using gamma and beta gamma. So I'm going to go directly to that notation of gamma plus gamma, beta. So we have that times this plus this times that. Except, forgive me again, I missed the vector term in these, so I need to move them. So this is sigma x right here. Now on the next step, what I will do is separate out all of the vectors from the bivectors, because if you have this vector times this vector, you're going to end up with a bivector, whereas this vector times a scalar is going to give you a vector. So I'm going to rewrite things over here. X r sigma x plus gamma, and this is just the y component, plus or sorry, that's the kind of, don't know why I did that, and then plus gamma, and then this right here. And then there are going to be the bivector terms. So in this one will end up with sigma xy. So we'll end up with ey, or end up with ey here, but then it'll be gamma times beta. So we end up with that. And then we're going to end up with an almost identical part here, except there's going to be an x and y right here, or there's going to be an xz, but the thing is that xz is actually the opposite. It's negative, or zx, and zx is actually the one used in the basis. So I'm going to delete that. And then we go over here, add gamma beta ez r sigma zx, and because it's zx, it's negative. So you end up with these components right here. And this gives you your new electric field. And cool enough, your electric field has actually smeared out a little bit and become a new magnetic field. So now there is a new magnetic field that didn't exist before. So in the rest frame, there's no magnetic field at all. But in the lab frame that's viewing this moving particle, they observe a magnetic field. So this is the result that you end up with. It is that you have an electric field and a magnetic field. Now, if you want to expand these out using Cartesian coordinates, you can. Just remember to replace the r, the position r here, using this rule right here, because it is a Lorentz. They are related by Lorentz transformations because they are different frames. But let's talk a little bit about why this happens. Well, I drew out a little diagram to show why. The reason is that when you're in the rest frame, it's symmetric. The fields are going out equally in all directions. So there's no change, it's just static. But when it's moving, if you look at it in the XY plane, then this is the X direction. The X direction ends up not being affected at all. It has the same strength, it moves and therefore like has the same strength. But all of the lines, the field lines that have components in the Y direction shift and it sweeps out. It sweeps out area. And this sweeping out of an area, well, that's very much like a bivector. It's a plane. So when you sweep out an area, you're creating a plane, which is creating a bivector, and that's what the magnetic field is. You can see that it does that on the XY, and it does that in the XZ plane, but because it's going X to Z, that's the opposite of going Z to X, so you end up with the negative sign here. But that is what is happening here. The field lines are being swept in time and creating magnetic fields. So let's zoom out so you can now see that. That is the problem and the solution. Well, I hope that this series was beneficial and maybe a little eye-opening to different things you can do with geometric algebra, especially in relativity. And you don't even have to use the space-time algebra. You can do it in just the most basic algebra for classical physics.